Today we continue to work on our tower blocks game. And what we want to achieve in today's episode is to have this nice and smooth camera movement, which we don't have. We have a jerky one, which I will show shortly. Right? And secondly, we want to have these chopped off or falling blocks, which we also don't have. So let's get started. First of all, let me remind you what we stopped at. So again, this is our current camera movement, which is just a jumpy one, right? Jerky. It simply jumps into the next position that the camera should be in without like the smooth movement. And secondly, we don't have any falling blocks or chopped off sections. So this is what we're going to do today, and I believe we can start with our camera position, because this is quite an easy thing to do. So we have this function, update camera position, which jumps to the next position and updates the target as well. Once the block is placed, right, the position instantly changes, the camera jumps, and it looks crappy. We would like to adjust it by using linear interpolation, saying that, all right, how about you take my current position and start moving towards this position based on some camera speed. Right, we can define the camera speed, something like 0.1, and same can be applied to our target. Camera target Y, please start moving towards this new value based on camera speed. Interestingly enough, that is all that is needed to achieve this smooth movement. As you can see, this linear interpolation moves us towards the next position, but not like in one step, but in many steps based on camera speed. Now the game is over, we need to move back to our initial block, and it should also happen smoothly. Alright, that looked pretty nice. So the next thing we need to do is we need to work on this falling blocks. We already have this block struct, but we will need to introduce a new one, which is going to describe how falling blocks operate. We will need to have, or we will need to know the position of the falling block. We will need to know its size. We will have its rotation based on each axis. Then there will be rotation speed, so how fast we rotate for each axis, right? So we have values for independently rotate around X, around Y, around Z. Then we will have velocity, pretty much just dropping it down, so some Y value, like gravity thingy. And we need to have the color of the block, and probably to keep track whether this falling block is active or not, because once the block is outside of our game screen, we don't really want to handle it anymore. All right, so we already have a function named CreateFallingBlock, and let's create a new function right below it and name it CreateFallingBlock. Here we simply remove this or return the struct with all these parameters that we need. We can start thinking like what we need here. So position needs to be supplied to us. Same goes for size, right? So whenever we want to create a falling block, we need to actually supply the position and size of the block. Rotation is initially 0, right? So we do not have any rotation when the chopping happens. Our rotation speed is something that we define randomly. Get random value let me type it out and then I can explain y and z. So pretty much we need to be working with radians, and this is the values from -300 up to 300 divided by 100. So the interval we generate for x, y, and z is from -3 up to 3. So you can think of it as minus pi to pi. We don't have like 314 or anything. And it defines how fast we rotate around the axes. Velocity can be static in the sense that we can tell, hey, please move down, right, at this kind of speed. Color needs to be supplied to us, and when we create, the block is actually active. All right, so next thing, we need to keep track of these falling blocks. So we need to add another property to our game structure. So this is going to be a list of falling blocks, which we need to initialize to null, right? And what else do we need? We need to, of course, learn how to draw them, and we need to actually learn how to create them. Right, so here is a place block function. I guess we can start with learning how to create the block. So if you remember, we have this section where we check for perfect overlay. If the difference is really small, the delta is really small, we can snap it to the underlying block, and then no chopped block is created. But otherwise, we are adjusting the size and position of our current block so that it's placed in correct place. And this is the exact place where we want to create our chopped or falling block. So let's see, we have something like chopped size is really our current size minus overlay, right? So if you remember, overlay is how much we have overlaid our current block with underlying 1, and current size is just our whole size. So this chopped size gives us the size of the area that, not the area, but the length that is outside of underlying block, and it needs to fall down. We can, of course, say that, right, if chopped size is like more than 1% of our initial block size, which is 10, only then we can create something, but we probably won't ever enter here because our perfect snap will hopefully should hopefully, yeah, catch it, but just in case we have it here. So we need to do something here, some magic, and finally we can say that, hey, let's push new falling block with some chopped position, chopped size. We already have that variable vec and current color, right? So we're putting the color of our current block. All right. What doesn't it like? Yep. All right, so what is chopped position? Chopped position, we need to calculate position, but we can take current position, and same for chopped size vec, we can grab current size. What we do need to do is to adjust the size based on the axis that we're working on and the position that we're working on. So again, we need to check if it's is axis, x-axis, or it's z-axis. So let's write it out for x-axis, and it will be pretty much the same for z, except that I will change dot x to dot z. And when we're dealing with the x-axis, first thing that we know is that chopped size x is going to be chopped size. Right? So if we're chopping off some part of our current block, we're chopping off we're first grabbing the full size current and then adjust the X to our chopped size. So same can be applied for Z. And then we need to check for deltas, right? So if delta is greater than 0 or else. So what does it mean if delta is greater than 0? It means that our block was moving on this x-axis and it has actually went further than the underlying block, and we need to chop off its head, our current block head. But if delta is negative, it means that our current block hasn't reached the head of underlying block, so we need to cut off its tail. So that is why we need to adjust the center. So we're adjusting the center, the position of our chopped block, which is current position. So this is the middle of our current block. Then we need to move to its head, right? So we need to take current size divided by 2, right? So current size is the full size of the current block. But if we take the middle, x position, x value middle, add half of it, so we end up at the head. And we know that we're chopping off this chopped size from here. And in order to have the center of this chopped size, we need to subtract not the full chopped size, but only half of it. And what happens if delta is negative? We need to go to our tail, which means we start in the middle of our current position. We need to subtract half of our size so that we're at the tail position, and then add half of our chopped size. And the same logic applies for Z. What we need to do is not to forget to add .z instead of .x. Now I do believe that this if-else can be written much shorter, because really there are only like signs playing based on some delta, but we can leave it like that for now. If we run it, everything should be fine, but really we don't see anything. Falling blocks are created, but we are not showing them. So we need to introduce a new function, DrawFallingBlocks. Oops. All right. We have a game. So first of all, we need to know the length of our falling blocks. Then we need to iterate over each falling block. And then we only operate on it in case it's actually active. Right? And we need to somehow draw rotated cube. Now the thing is, like if we use the draw cube, which we used in our like draw block, you can see that there is no way for us to supply the rotation, and we do want our blocks which are falling down to be rotating. Now there are a few ways we can handle it, and we can, for example, include RLGL and start applying some matrices. There is this rotateF function, but it's a bit different in a sense that it expects that we provide an angle and an axis based on XYZ around which you rotate. But as you saw, the FallingBlock struct that we have is actually a bit simpler, I would say, where we only define rotation for each axis, so that we would like to rotate, let's say, 2 radians around X, to like 3 radians around Y, and 1 around Z. So we don't actually calculate any angles, we don't calculate the axis around which we need to rotate. There is probably a way to convert one to another, but I haven't really explored that way, and I would like to show you a different way how we can draw the blocks, which is also useful for you to know. I really also didn't know about it before figuring it out, learning about it, so let me show you. First of all, let's jump into our game struct and introduce a new model, cube model. We can initialize it, cube model, come on, cube model. We can say load model from mesh, and then we can also generate mesh cube with some sizes, and it's going to be a simple cube, 1 by 1 by 1, right? We generate all the vertices, we load it as a model and store it inside cube model. Now, when we draw the thingies or the falling blocks, we can actually invoke draw model call and supply the cube model here. Then we can adjust its position, its scale, and set its color. But interestingly, we don't want to adjust the position, so we can say, hey, draw it at origin. We don't want to apply any scale, so draw it as it is right now. And for color, we can actually crop the falling blocks color. Now the interesting thing is that we can apply transformations, right? So not via this draw model call, but via game cube model transform, which expects us to provide a matrix for some local transformations. And this is exactly what we want to do, is we want to say that, hey, there is going to be a transform matrix where we're gonna matrix multiply something, matrix multiply something and something. So really, we will have 3 matrices, we will multiply them, we will receive a final transform matrix, and it's going to be applied to our cube model. So first of all, we would like to scale our 1 by 1 by 1 cube to the size of this falling block. Next, we would like to rotate it based on the rotation of this falling block. And finally, we would like to translate it to the block's position. Interestingly enough, it's quite easy to create these matrices. So let's do that. Raylib provides us everything that we need. So there is matrix scale. We need to provide the size of our falling block, block size X, block size Y, and block size Z. For rotation, we have matrix rotate. It has many different thingies here, and we're interested in XYZ. So this is just a rotation for each of the axes based on radians, and we have a nice rotation vector for that. And for translate, matrix translate. No. Yep, here it is. So we need to simply give it the position of our falling block. Position Y, block position Z. Right, so you need to also remember that the order matters. So first we want to scale, then rotate, and then translate, because it's done based on origin. And if you first translate and then rotate, it rotates like the world where this transformation happens, and you will end up with a different result. If you have been dabbling with OpenGL, you will see that usually there the order is reversed. You would write it like translate, rotate, and scale, so that scale applies first. So this is something to keep in mind. That's how Raylib operates. So we need to first provide the matrix that is going to be first applied to our model, then the second, the third, and so Alright, so nothing should really change, but we crashed. We added this model loading, and it probably crashed because we started the whole model loading before our Raylib has initialized all the OpenGL system and so on. So we need to make sure that our init game, where we do this cube model load mesh and stuff after the init window call. After that it works. We can already see these blocks that should be falling off, right? So let's restart it again. So let's see. We're gonna stop right here, and you can see this section which we already drew, and this is not part of this block here. This is actually falling block. It's just we do not animate it yet. We have successfully created it. We can check here again correctly chopped off, and yeah, you can see that we checked 4 sizes, or not sizes but 4 sides, and all of them correctly chop off the block. And now what's missing is of course the animation, and we can do that by introducing UpdateFallingBlocks game.d. Let's do that. UpdateFallingBlocks, which has a game and delta time. Now we can grab probably this start, so that we need to iterate over every single falling block. We are going to be working only with active ones. And what do we need to actually change? First of all, we need to apply some rotation, right? So our X rotation is increased by rotation speed X times delta time. Same for Y and Z. Then our block should also be falling down, so we need to apply velocity to our position times delta time, again for X, Y, and Z. And finally we can also check that if block position Y is less than something like this, we can say that block active false, and so we don't operate with it anymore after it's like way beyond outside of our screen. Let's run it. Moment of truth. Bam. It's falling. We don't have any physics, and I don't plan to add any physics engine, so it just falls through. Right? But the animation is there. Okay, interestingly enough, I think we can also draw, when we are drawing the falling blocks, we can have it wires also exists, except that we need to set the black color. Let's see how that goes. Yeah, looks a tiny bit better. Again, we are missing the lighting, we're missing the shadows, and that is going to be our next episode, where we're gonna work on a custom shader that is going to introduce the lighting into our game. We will avoid using these wires, which are like unreliable. You can sometimes see that they're not correctly drawn, and by introducing lighting we will see shading on our blocks, and it will be visually appealing and much easier to understand that this is the block, how it's spinning, how it's shown, and so on. I hope you enjoyed this episode. If you did, please like this video, and if you haven't yet, please do subscribe to my channel. It helps me greatly. Thank you, and I'll see you again. Bye.